Well, welcome back. We continue. No, we will not continue. We start with Guillem. We'll be talking about algebras and gravity. You have here the references, and you have Guillem.
Hi.
You have to monitor.
Let's go have an announcement regarding the asado. Regarding the asado, yes. 7 p.m. So, the guys from UBA, let know, because I know that you told me some students were coming. So, let them play now, not later. Okay? 7 p.m., the ones who haven't played, then. Me salió muy capuzoto. Bueno, but maybe. Sí, someone. We are asking to bring some plate and.
Hay que pagar, hay que transferir el comprobante a Guille. El que vaya a comer con plato y cubierto, traiga, si no comemos sanguchito.
Also bring some glass. And you bring the beverage.
Anótense el alias y el teléfono antes de que Guillem lo transforme en fórmula de.
Okay, so let's know the guys in Buenos Aires. Good. So Guillem, you're welcome.
Shall I start?
That's my number.
Well, thank you for inviting me. And well, I will talk about I will give you some introduction on this topic called von Neumann algebras and their role in QFT. And the idea is, so after that, I want to tell you a bit about some applications of the theory of von Neumann algebras to quantum gravity, which are, this has been a topic that Witten, Pennington, Liu, and other people have been working on the last years. Okay, so my idea is to give 2 lectures, one on algebras, and today I will talk about algebras and their role in QFT, and tomorrow my idea is to tell you some of these ideas by Witten and company on the application of the theory of von Neumann algebras to quantum gravity. Okay, so well, I recommend, so for those who are interested in this topic, in the topic of von Neumann algebras, I recommend these readings. Harlow, well, this is a paper by Harlow on another topic, but it has an appendix on von Neumann algebras, which is, I think, very nice. Because von Neumann algebras are a topic which very quickly gets too mathematical and too complicated, but all the complication comes from infinite dimension. And the appendix of Harlow is restricted only to finite dimension, and this makes things very easy. So for those who are interested, I recommend very much to start with Harlow. And then there is this recent review by Jonathan Source, which is very pedagogical. It's much better than for us physicists, it's much better than any book on von Neumann algebras. This is a recent review. And finally, so once you have all this background, you can read Witten's lectures, which are very nice. Okay? So what's a von Neumann algebra? So now I will give the definition, but what I would like to convey is that you know that in quantum mechanics, we're interested in entanglement, right? And entanglement is all about subsystems. So when one talks about entanglement, one is thinking about what happens to subsystems. Well, a von Neumann algebra is a generalization of the notion of subsystem in quantum mechanics. And it's a generalization that is useful, or even, I would say, necessary to study entanglement in quantum field theory. Okay? So this is the idea. And to introduce von Neumann algebras, let me think of a quantum system made out of 2 subsystems. Okay? Let's say subsystem 1 and subsystem 2. If I have this kind of system, the Hilbert space, of course, factorizes, right? I have a H1 times H2, and associated, sorry? This is an abstract, so I'm thinking about a quantum system. I'm talking about quantum mechanics, okay? It's not even QFT. It's a quantum system made out of 2 subsystems, 1 and 2. I use this drawing, but just 2 particles if you want, or 2 qubits, whatever, okay? So, well, the Hilbert space then, you know, how do I make the Hilbert space of 2 systems? Well, it's the tensor product. And, well, associated to one subsystem, let's say subsystem 1, there is naturally associated to this system, there is an algebra, which are the operators which only act on subsystem 1, right? So this I could call A1, the algebra naturally associated to subsystem 1, which is this algebra. The operators on H1 times the identity on H2, okay? So associated to this subsystem, I naturally have an algebra which is all the operators acting on this guy and doing nothing on the other guy. Okay? This B, just technical, this B stands for bounded because, well, one has to restrict to bounded operators because bounded means continuous. And you know that in general, operators are linear maps. In infinite dimension, everything which is linear is continuous. So linear means straight line, and this is continuous. But in infinite dimension, a linear map can be discontinuous. So one restricts to continuous maps, which means bounded operators, right? So this is the reason for this B here. But just think of all operators acting on subsystem 1. Well, this is a subalgebra of B of H. B of H is all operators on the whole Hilbert space, right? And this subalgebra satisfies certain properties which are easy to see. The first property is that it's, there are some properties. The first is that it's self-adjoint, meaning that each element of the algebra, if I have an element of the algebra, the adjoint is also in the algebra. Okay? So it's self-adjoint. Meaning that it contains the adjoints of all its elements. Okay, this is obvious that this algebra is self-adjoint. Another obvious property is that it contains the identity. Okay, and there is a third less obvious property, which is a topological property. And I will just say it but not prove it. And it's that it's closed in what's called the strong topology. In the strong or pointwise topology. And this, just so you know what this means, you know, an operator is a function, right? It's a particular type of function, a linear function. And you know that sequences of functions have, so there are two natural notions of convergence of a sequence of functions, right? You can have pointwise convergence or uniform convergence. So each of these notions defines a topology, and so this algebra is closed in the pointwise topology. So meaning that if I have a sequence of operators that converges pointwise to a certain operator, then that operator lies in the algebra. Okay, but it's just a technical thing that I have to call because it's true and it's important, but I won't pay much attention to this. Okay. Well, so this kind of property allows you to define functions of operators in the algebra. And this is something that, well, so at this level, this is just, I'm talking about a mathematical object, but in physics, you want to compute functions of your operators. So this allows you to define functions of your operators. Another thing one could say is that if you have a sequence of operators that converges pointwise to some operator, in principle, that limiting operator is indistinguishable physically from some operator which lies in the sequence, and then you would like that operator to be part of your algebra as well. But I take it just as a property of an object, a mathematical object. Well, so this leads me to the definition of what's a von Neumann algebra. A von Neumann algebra is a subalgebra of B of H, which has these three properties. Okay, so von Neumann algebra. So a subalgebra of B of H with these properties is called a von Neumann algebra. Okay, and I will abbreviate it as VNA. Okay, von Neumann algebra. So whenever I have a subsystem in quantum mechanics associated with this subsystem, I have a von Neumann algebra. But of course, not all von Neumann algebras will arise in this way. So this is why I say that von Neumann algebras are a generalization of the notion of subsystem. Every subsystem has a von Neumann algebra associated, but not all von Neumann algebras arise in this way. Okay, in this sense, it is in this sense that I say that VNAs generalize subsystems in quantum mechanics. Okay? Yeah.
Not very important, but you mentioned that this is like a point-wise conversion.
Yeah.
Can you phrase what would be like not point-wise, the other one?
Uniform.
The uniform. What would be the analog of uniform conversion? Like quantum mechanics. Like you mentioned that the point-wise is like a succession of operators.
So when you have a sequence of operators, there are two natural notions of what it means that this sequence converges.
Okay.
It can converge pointwise.
But what is pointwise?
Pointwise means that, so it's the same notion that you use in regular functions. Okay. So you know that, for instance, you can have a sequence of functions that goes like this and tends pointwise to a step.
No,
but
in functions I can see them, but as operators, how can you?
Pointwise means, so I can write it precisely. No, yeah.
Can you think of pointwise? I think I understand.
Okay.
I think I understand.
The uniform. Okay. I will.
Like the operators in all points.
Totally. Yeah. So you say that, well, a sequence of operators, let's say On tends to O pointwise if On psi tends to O psi for all psi. This is pointwise, okay? And uniform, and you say uniformly, if the norm of the difference, O minus On minus O, tends to 0. It's about the norm, okay? But just technical, I don't want to get too technical with it, okay? Well, it's difficult to erase this.
Try with the other eraser that you have.
Or not. Let's try. Brute force. Ah, ¿se puede dar vuelta y...? ¿Cuál? ¿Este se puede? Pero no sirve de nada. No, yo todavía tengo un poco de fuerza física. Gracias, Pedro. So, well, let me talk about one example of von Neumann algebra, which is called the commutant. Yeah. I don't know what topological entanglement entropy is. What's
Some
it?
kind of entanglement that appears, so it appears, it doesn't exist until you somehow cut your spec. I think it's more related to, so say you have a sphere,
Yeah.
and then you have a topological theory there, so you shouldn't find any entanglement, anything that would depend on, say, distances or anything like that. But it just so happens that when you cut the sphere into two,
there's entanglement between both sides.
Some kind, because of the non-local entanglement.
Okay.
It's a bit weird. It's something dire.
So, I mean, whenever you talk about entanglement, there is a von Neumann algebra involved. Because in some sense, at least if you have two subsystems, each subsystem will have associated a von Neumann algebra. But I don't know if there is a more specific.
In some kind of limbo where you don't
Well, then maybe that's relevant. Yeah. Then maybe that. Yeah. Okay. So, well, let me talk about one example, very important example of von Neumann algebra, which is the commutant. Okay. So the commutant, you give me a set of operators, any set you want of operators, and the commutant is simply all the operators that commute with everything in that set. Okay. So the commutant of a set, any set of a set, let's call it S in B of H, set of operators, it's denoted as S prime, and it means the set of all operators that commute with everything in S. Okay, this is the commutant. This is the commutant of a set. And there are two properties which are very easy to see of the commutant. The first property is the following. Properties. The first property is that if a set S is contained in another set T, then the commutants are contained the other way around. Then T prime is contained in S prime. This is very easy. So let's say that S is this, T is this. The commutant of T is what commutes with everything here. In particular, it commutes with S as well. Okay? So if S is contained in T, then the commutants are contained the other way around. And the other easy property is that S is contained in its bicommutant. This is also very easy to see. What this means is that among the things that commute with what commutes with S is S itself. Okay, it's a triviality. Okay, there are two simple properties of commutants. Well, another thing that one can easily see about commutants is that the commutant, no matter what S is, no matter what set S is, the commutant is already an algebra. First of all, the commutant of anything contains the identity. This is for sure. It contains the identity because the identity commutes with everything you give it, right? Another one, if I have two operators in the commutant, the sum of these operators and the product of these operators will also be in the commutant. Okay? What's not guaranteed in general is that the adjoint will also be, but if the original set is already self-adjoint, then the commutant will also be self-adjoint. So this means that if I have a set S, no matter what this set is, and I only ask it to be self-adjoint, then the commutant will be a von Neumann algebra. I didn't mention the topological property, but it's satisfied as well. Okay, so if S is self-adjoint, then S prime is a von Neumann algebra. This is a very easy way to construct von Neumann algebras. You give me a set which is self-adjoint, you give me one operator and it's adjoint, and then taking the commutant of that, I build a von Neumann algebra. Okay? This is a very easy way to construct von Neumann algebras. And there is a theorem, a famous theorem, which says that all von Neumann algebras arise in this way. This is not just an example of a von Neumann algebra, but this is the most general example of a von Neumann algebra. And this is called the bicommutant theorem. Bicommutant. The bicommutant theorem says that if I have a von Neumann algebra, let's say A is a von Neumann algebra, then the bicommutant of A is A itself. This is a theorem by von Neumann. You give me a von Neumann algebra, take the double commutant, and you will recover the original set you had. Okay? Yes. No, it means that it contains the adjoints of all its elements. So if you have an operator which commutes with some other operator, the dagger of your operator will commute with the dagger of the other operator. So if your original set was self-adjoint, for each operator you had the dagger of that operator, and then anything that commutes with the set will also commute. So the dagger of that will also commute with the set. Okay. So so this theorem, what it tells you is that you have a von Neumann algebra, and it's the commutant of something. What's that something? The commutant of that algebra you had. Okay. So the commutants are the most general example of a von Neumann algebra. And using these properties of commutants, we can easily find a corollary to this theorem, which I will prove now. Corollary. S2 prime, give me any set. When I speak about an algebra, I will write A, and when I speak about a generic set, I write S, okay? So give me any set. The bicommutant of this set is the smallest von Neumann algebra that contains that set. S2 primes is the smallest von Neumann algebra containing S. And this is very easy to see. The smallest in the sense that any algebra containing S will also contain S2 prime. In this sense. So that S2 primes is a von Neumann algebra, of course, because it's the commutant of something. Okay? That it contains S, of course. We already saw that. And what remains to be shown is that it's the smallest one, okay? So let's see this. Suppose that S is contained in some algebra, A. Okay? Then I take commutant and I use this property. I take commutants and I get that A prime is contained in S prime. And I take commutant again and I obtain that S2 primes is contained in A2 primes, but A2 primes is A. So what this is telling me is that whatever algebra contains your set, it will also contain the bicommutant of that set. And this means that S2 primes is the smallest von Neumann algebra containing S. Okay? Is it clear? Okay.
Then you can identify A with A double commutant, but not S with S double commutant, because A is an algebra, but S is not.
Exactly. So for instance, I give you one operator and its dagger to make the set self-adjoint. So it's clear that this is not an algebra. This does not contain the identity, for example. Okay. So this is commutants. Now let me talk about factors. What's called factors. Okay. A factor is a von Neumann algebra that has what it's called a trivial center. So factor. So an algebra A is a factor. If it satisfies this property, which means that this is the center of the algebra. The elements of the algebra that commute with the algebra, okay? So an algebra is called a factor if its center, that is the operators that commute, the operators of the algebra that commute with everything in the algebra, if this center is just the multiples of the identity. This is what's called a factor, okay? So meaning that if you find an operator in the algebra that commutes with everything else in the algebra, this operator, it must be a multiple of the identity, okay? So the algebra I introduced at the beginning, this A1, times identity 2, this algebra, the algebra associated to a subsystem, is a factor. This is a factor. And this is, I will ask you, what's the commutant of this algebra? So what are the operators that commute with this algebra? On the second, right? So the commutant of A1 is identity in the first times operators in the second. So what's in the center? What's in this algebra that is also here? The identity. Okay? So this is an example of a factor. And this is why factors are called this way, because, yes. But the B is everything. What do you have in H1? What operator do you have on H1 that commutes with all operators in H1? Only the identity.
No, perhaps
It's very easy to see. No, but I don't have to assume anything like that. So I mean, but because this B of H is not any algebra. This is all operators. Okay, and the only operator that commutes with absolutely all operators is the identity. That's the reason. Well, this is an example of a factor. Okay, and the factors that but again, this is an example of a factor, but not all factors arise in this way. Okay, the factors that are obtained in this way are called type 1. So factors arising this way are called type 1. Okay, type 1 factors are those factors that are constructed in this way, associated to subsystems in quantum mechanics.
What's the role of C?
The C means that, so this means the multiples of the identity, not just the identity alone, but the multiples.
How can that appear
in this example? Well, because that's so if I want an operator that lies here and also here, I want to put, so you would say, well, I have to choose the identity here and the identity here, right? But I can also choose 3 times the identity here and 3 times the identity here. So the operator 3 times the identity can be written in this way and also in this way. Yeah? Okay, so factors arising in this way are called type 1. And now let me, yeah. Totally. Yeah. Good. So, in principle, to construct an algebra, what I have to do is take a set and take the commutant of that set. It's not guaranteed that the algebra you will get will have this form, will be associated to a factorization of the Hilbert space. In general, it will not. This is just one example of a von Neumann algebra, but you can find other examples. Okay, so arising in this way means, let's say, factors that you can think of as being operators associated to a subsystem in quantum mechanics. Yeah.
You construct a von Neumann algebra, and it's possible that it does not have a test invariant subspace. A space that when you multiply
Totally.
it with all operators of the algebra is invariant.
No, so, well, this algebra, so you can find algebras that leave subspaces invariant but don't have this form. For example, let me give you an example. Matrices, block diagonal, 0 here, and here anything, and here anything. This leaves two subspaces invariant, but it doesn't have this form. For instance, do you agree that this algebra has two subspaces invariant? Two invariant subspaces. So the vectors which only have support here and zeros here are invariant. So form an invariant subspace, and here you have another. But this doesn't have this form. For example, the commutant of this is multiples of the identity here and different multiples of the identity here. So the commutant is bigger than just, this is not a factor. Okay? So, okay. Well, so these factors that you obtain in this way are called type 1, okay? These are the kind of algebras one deals with when one does entanglement in quantum mechanics. You have a subsystem, you have two subsystems, and to each subsystem you have an algebra of this kind, and you can do all kinds of things, okay? So, let's think about a little bit about this algebra, and imagine that the second Hilbert space has infinite dimension. It may happen that H2, the Hilbert space on which this identity acts, has infinite dimension. Then no operator in this algebra will have finite trace. The trace of all these operators will be infinite because there is a factor which is the identity which has infinite dimension, right? So in this algebra, if the second Hilbert space has infinite dimension, there are no operators with finite trace. But still, I can define a modified trace which satisfies all the properties of a trace, which is just trace on this part of the algebra. So let me write it. So an observation, the trace may not be well defined. Defined on A1, on this algebra. But let's let me use the letter tau. This thing, tau of, let's say, x1 times 1, 2 equal the trace of x1. So this map, which is not a trace, it's a modified trace, this satisfies all the essential properties of the trace. Okay? This map satisfies all the essential properties of a trace. Meaning, it's cyclic, because it's in the end it's a trace, okay? It's cyclic, it satisfies tau of AB is equal to tau of BA, cyclic. And another property it satisfies is that tau of A daga A is positive for any A different from 0. So if you give me an operator which is positive, strictly positive, which is this A dagger A, the trace will give you a strictly positive number, okay? These are, let's say, the essential properties of a trace. And of course, this map satisfies it because it's, in the end, it's not exactly a trace, but it's almost that, okay? So the conclusion of that is that on a factor of type 1, I can define a trace. I can define a map which has all the essential properties of a trace. Okay? And I can use this trace to define density matrices and entanglement entropies. Because a density matrix, you know, it's something that has trace 1. So before defining a density matrix, I need to have a trace. Okay? So this trace, this, let's say, modified trace can be used to define density matrices entropies and all that. Okay? So factors of type 1 are those that arise in this way. And on these kind of factors, I have a notion of a trace which I can use to compute entanglement entropies. Okay?
So there, the left part
I don't need that it has finite dimension. If it's infinite dimensional, this will mean that there will be some operators which won't have a finite trace, but still there will be plenty of operators which will have a finite trace. This is what happens in the ordinary. I mean, so any operator which has a finite number of non-zero eigenvalues will have a finite trace. And with these kind of operators, you can approximate any operator. So I'm not claiming that all operators here have a well-defined modified trace, but let's say plenty of them have a well-defined modified trace. Okay? Whereas the unmodified trace, none of them. So no operator here, if H2 is infinite dimensional, no operator here has a well-defined unmodified trace. Okay? So well, all this I say because, well, first of all, because it makes connection with, so the trace is crucial in order to speak about entanglement, or well, at least in order to compute things as entanglement entropies, because the entanglement entropy is trace of row log row. I need a row, and in order to have a row, I need a trace. Okay, so well, this is the thing, and this leads me to the other two types of factors. One says that a factor, yeah.
the modified trace is unique, or is it there are many modified?
Well, there is a theorem saying that if you have a factor, there is only one possible modified trace up to a global factor. So it's essentially unique. Yeah. Well, okay, so then a factor is said to be of type 2, if it's not of this, if it's not type 1, if it doesn't arise in this way, but still admits a modified trace. Okay? So it's of type 2 if it's not type 1, but still admit a trace. Okay? So in a factor of type, if I have a factor of type 2, so it doesn't arise in that way, but still I can define a trace, and hence I can define density matrices in that factor. Okay? So it means a trace, and therefore density matrices. Yes.
When you say it does not arise in the one, that the C number has maybe a C number or another.
No. So any algebra which has this property is a factor. This algebra is an example of an algebra that has this property, but it's just an example. All these examples form type 1. But then I can have other factors which are not type 1. And if I have a factor which is not type 1, but admits a trace, then I call it type 2. And if it doesn't admit a trace, I call it type 3. And this is the type classification of von Neumann algebras. Okay? And so one says it's type 3. Okay, yeah. Admit a trace. Okay, I'll give an example. I'll just say things. I won't prove anything, okay? How much time do I have? We don't have to talk about QFT yet. Ah, buenísimo. So let me give an example. Example. Think of the following system. So imagine an infinite set of qubit pairs. Okay, so infinitely many qubit pairs. Let's think of this system as, I don't know, this is one pair, another pair, another pair, and so on. Okay? So each dot here is a qubit. Okay? Or a spin up, down, whatever. Okay? I'm drawing the system. Okay. Or spin pairs, or whatever you want to call it. Okay? So what's the Hilbert of the system? In principle, one would say that the Hilbert is just the tensor product of the Hilberts of all qubit pairs, right? So one would say that the Hilbert is this thing, H1. Let's say that, let's number the pairs, okay? Let's say that this is the pair 1, the pair 2, pair 3, and there are infinitely many of them. So one would say that the Hilbert is H1 times H2 times etc. Okay? But this Hilbert space is not separable. You know, separable means that it has a countable basis. And in general, I don't know exactly why, but we don't like non-separable Hilbert spaces. What's for sure is that we never work with non-separable Hilbert spaces. I don't know what would go so wrong if we worked with a non-separable Hilbert space, but let's stick to this lore and reject non-separable Hilbert spaces. Well, you can easily understand why this is non-separable. I'll try to say it just using words, okay? This thing, a basis of this thing, what's the basis of this thing? You have to choose, so let's say that each of these Hilberts has dimension 4, right? Because each of these Hilberts corresponds to a qubit pair. And a qubit pair, so it has 4 possible states, okay? So in order to construct a basis of this thing, what I would choose is one, so I would take a basis of the Hilbert of the qubit pair, and then, you know, adjoin, so I would write something like this. So a basis would be, I know, I1, I2, I3, and so on, right? Where these i's go from 1 to 4. That would be a basis of this Hilbert space, okay? This is an infinite sequence of numbers between 1 and 4, okay? This is essentially the same as a real number between 0 and between 0 and 1. A real number between 0 and 1 is something like point something, 1, 2, 4, 6, 7, 1, 3. So a real number between 0 and 1 is a sequence of numbers between 0 and 9. Right? This is essentially the same. This is uncountable. Okay? So this Hilbert space is non-separable because its bases are uncountable. We don't like that. In order to get rid of that, what we do is reduce the Hilbert space and say, so this is non-separable. And then what we do is we take the Hilbert to be the span of the following way. Span of vectors of this form, psi1, psi2, etc. So this is a vector of this qubit pair, this of this other qubit pair, where we demand that all these vectors, so we demand that of all these vectors, only a finite number of them be different from a fixed vector we choose. So let's say psi I is equal to psi for almost every I. So what I mean here, so the Hilbert of this system is essentially the same as the tensor product, but where my allowed vectors are of the form corresponding to a vector to a tensor product, but where I demand that only finitely many of this psi I be different from a fixed vector I choose. So what I mean is, of these qubit pairs, the huge majority of them are in a fixed state, and only finitely many I allow them to choose another state.
Okay, so what you're saying is that suppose I had this set of many, not infinite because I can, but many.
Okay.
Mathematically, I would rather choose with a restricted Hilbert space rather than the full physical Hilbert space. The trick only works if they are infinite.
Mm-hmm.
Okay.
If they're finite, there's no problem with separability.
Okay.
If they're infinitely many, I have to do something in order to get a separable Hilbert space. And what I do is this. I fix, so I say that only finitely many of these qubit pairs are in a state different from a fixed state I choose by hand, psi. Okay? Yeah.
Why do you need them to be qubit pairs for this argument? Shouldn't they just be qubit?
So for this argument, I still didn't use that they were qubit pairs, but now I'm going to use it. So now I'll just mention the thing and not prove anything, but let's say that I choose this subsystem. So from all the qubit pairs, I choose the left qubit of each pair, okay? So let's say that this is the left system. So it turns out that the algebra of this left system, the algebra associated with the qubits on the left, is type 1 if this psi is product. So I remind you, I construct the Hilbert space by demanding that only finitely many of these qubit pairs be in a free state different from one state I choose. So the construction of the Hilbert space and of everything depends on what state I choose for the vast majority of qubit pairs to be in that state, okay? So if this state I choose is product, then the algebra of the left qubits is type 1. It is type 2 if this psi is maximally entangled. And it's type 3 otherwise. So in this simple system, you have all possibilities for factors.
What's the trace you can define?
what's the trace? You can define in type 2. That's a great idea. So the trace, what it turns out that it's, consider this state. So the state corresponding to all qubit pairs being in the reference state you chose. This is a possible state, obviously. You compute the expectation value in this state, and it satisfies the properties of a trace. Basically, because you are computing expectation values of something here, and for computing expectation values of things here, you can take the partial trace, and what you get from a maximally entangled state is the identity. And this is why you have the property of a trace.
That doesn't work.
No, because I mean, if I choose so I'm just I didn't plan to give this example, but what I mean is, so I'm not proving anything, but I think you can get the flavor that if I compute expectation values of left spins in this state, these expectation values will be tracial. Why? Because in order to compute an expectation value of something here, I can take the partial trace of every qubit pair, and if the if the state of the pair is maximally entangled, the partial trace gives me the identity 1, and then that's why I have a tracial state. But if this psi were anything different from maximally entangled, then when I compute the partial trace, I don't get 1, and then I don't get this symmetry under exchange, cyclicity. Is it clear? Or? Well, in any case, this is true. I mean, here you have an example. You have an example of 3 algebras of each of one different type. Okay. So now let me tell you about QFT, the role of this in QFT. Yeah. In many body. So of course, yeah. Here, imagine that we had a finite number of qubit pairs. Then we could have taken just the regular tensor product of Hilbert spaces, and the algebra corresponding to the left qubits would be type 1. So all the richness comes from having infinitely many qubit pairs. Okay?
Type 2 and type 3 are different ways of taking
So, well, in a sense, yeah. So if I had a finite number of qubit pairs, by this construction, I wouldn't get a type 2 algebra or a type 3 algebra. Okay? So I would say that type 2 algebras and type 3 algebras arise naturally when you have infinite number of degrees of freedom. And this, I think, is basically the reason why the local algebras of QFT are type 3, which is what I'm going to discuss now. So you see that type 2 is somewhat marginal. You need a state which is maximally entangled. This is very restrictive. If you have anything else, you get type 3. So type 3 is quite generic when you have an infinite number of degrees of freedom. So what people in condensed matter find, or many body, I don't know. I think that once I heard that type 2 was quite common in that area, but I don't know why. So let me talk a bit about QFT, the role of all these in QFT. And the thing is, in QFT, we have a natural way to assign a von Neumann. So now I will use everything that I said up to now. And in QFT, we have a natural way to assign a von Neumann algebra to each space-time region. So say that I have, this is the space-time, x and t, I choose some region, R, and I can associate an algebra to this region, which is simply the following. Take the field operators localized in R. Okay? Take the field operators evaluated at points in R, and well, this is not an algebra, this is just a set. Well, take double commutant. This is a natural way to assign a von Neumann algebra to each spacetime region in QFT. Okay, well, there are technical things here. First, that phi of x is not really an operator in quantum field theory. You have to smear it, but well, you can turn this into a rigorous thing. You can say, okay, instead of talking about fields evaluated at points in R, just fields smeared with functions with support in R. Okay, and once you do that, you get well-defined operators, but they're not bounded. Well, no problem. You can just take the imaginary exponentials and you get unitaries, and these are bounded. Okay, so this is a bit sloppy, but there is a way to make this more rigorous. Okay, so yeah, yeah.
Say you take your system with a finite number.
Yeah.
But you still define your Hilbert space like that. Then the claim is that that's not interesting, or that if you want to define traits like you did, then that's secretly type 1. Notice.
Good question. So I don't think I can define the Hilbert space like that if I have a finite number, because note that here what I'm saying is that only finitely many are in a state different from psi. If I had a finite number of qubit pairs, how would you define that? I don't know. What were you saying? Okay. Okay, so now let's talk about QFT. We have this. In QFT, we have a natural way to assign algebras to regions. And when we talk about entanglement in QFT, we are thinking, so this is the kind of, between quotes, subsystem we have in mind. So I compute the entanglement entropy of a region, and what I'm actually trying to compute is the entanglement entropy of this algebra associated to that region. Okay? But in order for that to make sense, I would need to define density matrices in that algebra, and for that I would need a trace, and for that I would need the algebra not to be type 3. Okay? But now I'll discuss a bit more. So okay, now this assignment of algebras to regions has several very easy properties. Let me discuss them. Properties. The first is that this is trivial. If R1, let's say, is contained in R2, then the algebras satisfy this inclusion. That's obvious. Another one is causality. If the regions are space-like separated, the algebras commute. Okay? If R1 and R2 are space-like separated, then the algebras commute, which now I can write in this way. The algebra of R1 is in the commutant of the algebra of R2. This is just a short way of saying that both algebras commute. Okay? This is all. I mean, it's trivial. And a third property I want to discuss is the following. Well, here I chose an arbitrary space-time region, but the kind of regions one usually chooses is the following. So a typical type of region is the typical region is of the following kind. You take a constant time slice, it's constant time, okay, and you choose some region of this constant time slice, let's say this, and then you take, the domain of dependence, the Cauchy development, which is basically this diamond here. This is the typical region one considers. Let's say this R. Okay. So the third property I wanted to discuss is that the algebra of R is the same as the algebra of, let's say, this small region here. Let me call this small region R, small r. The algebra of the whole diamond is equal to the algebra of the little strip around the segment. And why is that? So the statement is that the algebra of the whole region is the same as the algebra of the small region. And why is that? This is very easy because, suppose that I have a field operator here. This operator obeys some dynamical equation, which I assume, of course, relativistic. Okay, so since it obeys that dynamical equation, it's the value of the field, let's say here, is determined by what happens here. The dynamical equation tells me that the field operator evaluated here can be written somehow in terms of some initial conditions, which by relativistic invariance should have only, I only need initial conditions here in the past light cone of the point. So the operator here can be written in terms of operators there, and that's why I have this equality. Okay, any operator you can build in this diamond, capital or big R, can also be written in terms of operators in the small strip. Okay? Yeah.
Do you know if you can be derived also in the white man setting? You are not assuming nothing.
No. So only from Whiteman axioms you don't get that.
So there are statements.
Yeah. So in order to get that, you need to have a T mu nu. If you don't have a T mu nu, you don't get that. That's what you were going to say? Okay. Well, I'm being, so the thing is, as I said before, this is not well defined. I have to smear, and in general, I have to smear in something which is open, and that's why. But well, if I'm talking, for instance, about free fields can be smeared in a codimension 1 surface, and then for free fields, I don't need to draw this small neighborhood of the. Okay.
Can I make a comment?
Yeah, of course.
You can also think that you need, for a second order equation, you need the field and the first derivative. So if you only give the field equal 0, like the.
No, but you can have the momenta here as well.
Exactly, the momentum.
But for the momenta, you don't need to have this buffer zone.
No, but the buffer gives you a way to derivate and obtain the same information. If you make it infinitely slice, you only get 5. But as soon as you make it a little bit fast, you get phi and pi. You know what I mean?
But you can think of pi as an operator on the slice, as Damian was using it before with the extrinsic curvature, like analogous to that. But well, the reason is that you have to smear in something bigger than. So no, I'm just saying that this is what happens in as long as you have a T mu nu.
But there are non-local that don't have a.
Yeah. Okay. The Whiteman field theories with yeah. So I'm excluding that. Okay. For the argument I'm going to make now, I will exclude that possibility. So I will close this talk with 3 observations. And the first observation is that I forgot to mention one property. Let me write one other property. This is And the last property I want to mention is that the algebra of the whole spacetime is everything, is B of H. The algebra of the whole spacetime is everything, and this you can derive from Weightman axioms. I won't get into that, but so Weightman axioms, so from Weightman axioms you get that the fields act irreducibly on the Hilbert space. So if you have an operator which commutes with all field operators, then the operator is the identity. So the algebra of the whole spacetime is the bicommutant. So you take the commutant of the identity, and then this is B of H. Okay, so this is a property of. So, well, Weightman axioms are formulated in Minkowski, but I would say that this you can take this as a general statement. So, what I want to stress is that the algebra of everything is all operators, and this is an example of a type 1 algebra. This is a B of H in the whole Hilbert times the identity in a one-dimensional factor, let's say. So this is type 1. Okay, so I want to stress this because I will use it tomorrow. The algebra of the whole spacetime is all operators, and this is an example of a type 1 algebra. Okay, and now I come to these observations. The first is that the QFT algebras are factors. And this, I think we can get the feeling of this quite easily, I hope. And let me discuss this. Consider a region of this, one of these typical regions, okay? And remember, what does it mean to be a factor? A factor means that if I have an operator in this algebra which commutes with everything in the algebra, it must be the identity. Okay? So suppose that I have an operator, let's call this R, an operator that lies in the center of the algebra of R. Okay, suppose that I have an operator that lies in the center of this algebra. I want to show that this operator is the identity. Okay? Well, this operator which lies in the center will commute with everything in the algebra by definition, and in particular it will commute with everything in this stripe, right? Okay. But at the same time, this algebra commutes with everything that's space-like separated. So my operator A will also commute with everything in the rest of the stripe. Okay. If I have an operator in the center of this algebra, it will commute with all the stripe. Let's call this S. Okay. So if I have an operator in the center, this operator A commutes with the algebra of S. Okay, but the algebra of S, it's the same as the algebra of the causal development of S, and the causal development of S is everything. So this is the commutant of whole spacetime. And the algebra of the whole spacetime is everything, so this is the commutant of everything is just the identity. So local algebras in QFT are factors. Okay, the first observation. The second observation. So two of this I was able to, I think I was able to explain you why this is the case. The second, I will also be able, I hope, to explain you why it's the case. The third, I will just have to give it as a fact, okay? But the second observation, relation 2, is that these factors are not type 1. And to see this, let's again think of this typical region. Okay. And let's think of 2 points, 1 point here and 1 point in the complement, but very close to each other. Let's say X and Y. Okay. Let's think of these 2 points. And this is R. So if AR were type 1, if the algebra of my region were type 1, this would mean that I can obtain it from a tensor product decomposition, right? And if I can obtain this algebra from a tensor product decomposition, this means that there must exist a product state. Because in a tensor product, the tensor product is spanned by the product states. Okay? So if there was a tensor product decomposition giving rise to this algebra, then there should be a product state. Okay? So if AR was type 1, then there should exist a product state. Let's call it psi. And what would happen in that product state? Let me compute the 2-point function in that product state. Phi of x, phi of y. Let me think about the connected 2-point function. The 2-point function where you subtract the product of expectation values. So in a product state, the expectation value of the product is the product of expectation values. This is what happens in a product state. So this would be 0. Okay, because this is the connected part where I subtract the product of expectation values. So if the algebra was type 1, there would be a product state. And in that product state, I would get that this connected 2-point function is 0. Okay? But this property is extremely clearly not satisfied by the vacuum. So, but in the vacuum, let's say, let me think of one situation. Let me think that I send x and y to the common boundary. Let's call this P, the boundary between R and its complement. So in the vacuum, we know that what happens when I send x and y to P, what happens? Can you tell me? It's connected. It diverges because it's the UV divergence. When I send x and y to P, x and y become, I'm taking the coincidence limit. In that limit, the 2-point function goes to infinity. It diverges. Okay? So in the vacuum, this property is very much not satisfied. What happens is that if I choose appropriately the points x and y, it diverges. Okay? And more than that, all states in QFT are the same as the vacuum in the UV. Do I need to explain this or? Yeah. So, well, I'm thinking about reasonable states, okay? So when I think of if I think of a reasonable state, that state should have finite energy. And if I think of a free, let's think of a free field theory, finite energy means that not all modes can be occupied. Because if I had, if I had all modes occupied, then for sure I would have infinite energy. Because the energy is the sum of the energy of each mode. And, well, if I send the momentum of the mode to infinity, at some point, that mode should not be occupied because otherwise the energy would give me infinity. Well, let me think. So you say, okay, so I take a superposition of, and well, but still, it doesn't affect my argument, like at least qualitatively, because what this main function you're using has to go to 0 when k goes to infinity, and k going to infinity is the UV. So in the UV, the states in the modes in the UV are not occupied. So this means that any state, any reasonable state in quantum field theory, behaves the same way as the vacuum in the UV. Okay? You can also use the OPE to think about this. Okay, the leading divergence of a product of operators is always proportional to the identity, which means that it's independent of the state. Okay? So, and all states are equal to the vacuum, to omega in the UV. So this means that there is no state with these properties. So this psi doesn't exist, and therefore AR is not type 1. Of course, this is not a rigorous mathematical argument, okay? I'm not trying to do that kind of arguments. I'm just trying to make things plausible to you.
What do you mean by reasonable state?
So I think that so I couldn't accept a state with infinite energy. For one thing, that state would destroy the spacetime, wouldn't it? By gravitational back reaction. But even I think that if you take a more mathematical point of view, even that, I think that when, for instance, when you define the Fock space of a free field theory, you start with finite linear combinations of particle states, and then you complete that to a Hilbert space, which means that very high momenta are very much suppressed. So I think you can give a more mathematical justification for the fact that all states coincide with the vacuum in the UV. Yes. Tengo menos 5 minutos, ya. Puedo escribir una cosa más y... Sorry. I'll say one last thing. And so I made 2 observations which were, well, more or less justified. And the third, I won't be able to give any justification, but I will give some references. And the observation 3, and this is work by Araki, Bredenhagen, many people in the algebraic quantum field theory, and others, is that they are type 3. So this is something that has cost a lot of work in many years. I think that you can get a feeling of that by the generic. So in the example we saw that type 3 was generic when I had an infinite number of degrees of freedom. So this feature of the local algebras of QFT doesn't surprise me. I find it natural. But well, the real way in which it is proved, I mean, it's a very complicated thing. But well, this is something which is accepted, that the local algebras of QFT are type 3. And if they are type 3, this means that there is no possible way to define an algebra, to define a trace on these algebras. There is no reasonable definition of a trace for these algebras. Then there is no possible notion of a density matrix, and then there is no possible notion of entanglement entropy. The way I interpret this result is that there is no sensible way to renormalize the entanglement entropy. You can renormalize it if you want, you can subtract the divergences, but what you get you will not be able to interpret that as some trace of rho log rho. Okay? So my interpretation of this is that there is no sensible way. No, well. Well, So let's say
You find quantities that are independent and finite.
Yeah.
Why do you want?
If you, so I mean, I'm not saying that I have to interpret them in that way. So for instance, I take an entanglement entropy in QFT, which has many terms which are divergent. I just subtract them. I get something finite, and that's okay. You can work with that. You can extract a lot of information from that. You can prove the C theorem from that. But what I'm trying to say is that you cannot interpret that as an entropy. You don't need to if you don't want. But
Well, let me turn the question around.
okay.
What do you gain by having a well-defined?
Well, I just gain understanding how QFTs work. So it's not possible to think of a density matrix for a local algebra in QFT.
It's an statement about all possible operators, not just the one.
Even, I mean, yeah, you cannot think of a density matrix for a local algebra in QFT.
I think that you can probably define an entropy, but you want to generalize the trace operation that you are doing to define that to be able to act on any other operator, then you can.
Right.
Also, if you know something is an entropy, you do gain, right? Because you get a notion of micro. You know how many states.
So for instance, let me go a step ahead.
I don't know if you will lottery,
but the black hole entropy, you certainly would like to interpret it as something like log omega or.
Like first, you will have an enormous entropy. The limit, the classical limit will be infinite, that you cannot say anything about that. And then you will be able to interpret this little finite piece.
But I mean,
it's not a area over 4G that will be interpreted. Little quantum field theory piece.
Mm-hmm.
I don't know. When you say that the code thing was type 1, or I
Sorry?
The whole space was type 1.
Yeah, type 1.
So that's why we're writing.
Again, please, I didn't.
Is it related to the fact that we can do thermal?
Yeah, well, in fact, with thermal states, in principle, there shouldn't be a problem with the algebra of everything, but there is a problem with the fact that you have infinite volume. So say that I think that my spacetime is just a cylinder, where space is something with finite volume. There's absolutely no problem with thermal states. So there is a problem with thermal state, but due to infinite volume, it's the same as, the thermodynamic limit. When you compute a partition function in statistical physics, the log of the partition function is the free energy, which is extensive. It goes like n. When you take n to infinity, the partition function diverges, and everything kind of becomes ill-defined. This makes the algebra of everything complicated for thermal states when you have infinite volume. But there's no problem when you have finite volume. And that's the reason, yeah, that you have a type 1 algebra. Okay.
When you say, I will show you that this cannot be a product state because
yeah.
This statement like one state localized in R, one but can be another product.
No, but I mean, if the algebra here, let me elaborate on that. If the algebra here was type 1, there would be a factor decomposition of the Hilbert space, so that this algebra is the operators acting on one factor, okay, and the commutant is the operators acting on the other factor. This is in the commutant. So then this should happen. Because the point y is not any point, it's a point belonging to the algebra of the commutant. So belonging to a region whose algebra is the commutant.